Welcome to the Shape of Space Linear Algebra lesson on projections. Before we get to projections, we need a few concepts. The first one is the dot product. I have that up here. So if we have two vectors from Rn, the dot product, written u dot v, is the product of the first two elements plus the product of the second two, and so on. And what you get is a scalar. For an n-dimensional vector space V other than Rn, we can use the representation of the vectors in V to define the dot product. Two vectors are orthogonal if their dot product is 0. Given an n-dimensional vector space V, the vectors in the set M, k vectors, are said to be mutually orthogonal if the dot product of the representation of each pair of vectors from M is 0. So you see here we've taken V sub I and V sub j, represented them in terms of the basis S, and if the dot product is 0 for all ij between 1 and k, then this set here is said to be mutually orthogonal. The reason we talk about this, it's normally easier to work with an mutually orthogonal set of vectors, and in fact we'd like to have a basis that where all the vectors are mutually orthogonal. We'll get to that definition in a bit, but that's the motivation for going down this path. So if you don't have a orthogonal set of vectors, we want to eventually talk about a way of making them orthogonal by adjusting them a bit, and we'll get to that towards the end of this lesson. Okay, so we have another definition here. The orthogonal projection of vector v onto the line spanned by vector u is defined to be this vector here. So it's just a scalar. This quotient here is a scalar, and then u is a vector. So I'll show you what this looks like in 2 dimensions, just to give you a sense of what we're saying here, and that's on the next slide. In this diagram, I'm showing the projection of vector v onto the line formed by vector u. The idea is that you line up u and v to have their tails at the origin, and then you drop a perpendicular from the tip or the arrow in v down to the line formed by u. U could be smaller, could be over here, it could be out here, and the way it's drawn here, it's bigger. So we come down, drop a perpendicular. Now we want to find this length here, this vector. So it's alpha times u. And this perpendicular line is v minus alpha times u. So what we want is the dot product of u was with v minus alpha times u, this expression here, equal to 0, because we want these two to be perpendicular. And this expression here is the same as this, because you can distribute the dot product. So it's v dot u dot v, minus alpha times u dot u. We want that to equal 0. And we have, these are all scalars. This is a scalar, alpha is a scalar, and this is a scalar. It equals 0. So we could just add this to the other side and then divide by the dot product of u with itself, and then we get the value for alpha. So the projection of v onto u is alpha times u, or this, what we've solved for alpha. So that this here is this. And what you have is two orthogonal vectors at that point. You have the projection of u onto v, and you have this vector here, v minus the projection of u onto v. Okay, so let's continue. We have a couple of short theorems, or at least short to prove on this slide. Any set of non-zero and mutually orthogonal vectors is an n-dimensional in an n-dimensional vector space are linearly independent. So consider any linear combination of vectors that equals 0. We have this here. Take the dot product of v sub I with both sides. And since we assumed they were orthogonal, all the terms drop out except for this term here. And then we have this equals 0, and then we can just divide this scalar into 0, and then that implies that a sub I equals 0. And we can do that for any v sub I. So that forces all the coefficients to be 0, which implies that the set is linearly independent. Okay, and I use the property again of distributing the dot product across the sum. I didn't prove that, but that's one of the properties of dot product. Okay, and the second theorem follows from the first pretty much. In an n-dimensional vector space, V, if the vectors in a set S of size n are mutually orthogonal and non-zero, then the set is a basis for the vector space. So as we saw from the previous theorem, the vectors in S are linearly independent. And then by theorem 18, they form the set S forms a basis for V. And I just copied theorem 18 down here just to remind you. In an n-dimensional vector space, a set of n linearly independent vectors if and only if F spans V. So spanning implies independence, and independence implies spanning, assuming you have the same number of vectors as you have for the dimension of your vector space, which is what we needed here. We have a few more definitions on this slide. A basis for a vector space consisting of mutually orthogonal vectors is referred to as an orthogonal basis. As I mentioned earlier, that's desirable, and there's a way of creating this if you don't have it already from a given basis. We'll talk about that at the end of the lecture. A normed vector space is a vector space over which a norm or a length function has been defined. In terms of notation, we write the norm of V, an element of vector space V, this way here. The norm maps each vector to a positive real number, a length basically, and satisfies the following conditions. So it's the norm of every vector is greater than or equal to 0. The norm equals 0 if and only if you're talking about the 0 vector. For every alpha in R, so every scalar, and V an element of our vector space, you can factor out the scalar, and it's just the absolute value of the scalar. And if you're talking about, I mentioned R here, but if you took your scalar from the complex numbers, then it would be the absolute value of the complex number, which is the square root of each, the imaginary part squared and plus the real part squared. And then we have the triangle inequality. So the norm of u plus v is less than or equal to the norm of u plus the norm of v. Okay, and that if you have a norm that satisfies these properties, then for a given vector space, then you have a norm vector space. I have a few examples of norms on this slide. I'll start with Rn. If you take a vector v from Rn, the standard Euclidean norm is just the square root of each component squared added together, so this expression. For complex numbers, the n-dimensional complex vector space Cn. We have almost the same thing, except instead of having the each complex number squared, we take the modulus of the complex number and square that, and then we add all those together. We also have what are called the LP norms that can be used to as a norm for Rn and Cn, and of course P going between 1 and infinity. The LP norms are defined here. It's just the absolute value of each component raised to the P power, and then you sum those together and raise the whole thing to the 1 over P power. So these are the absolute value if you're talking about Rn, and if you're talking about Cn, then these would be the modulus of each components to the P power. Then there's also the L infinity norm, which is just the max of each absolute value for Rn, or the max for each modulus if you're talking about complex numbers. Given a mutually orthogonal set of vectors that form a basis for a vector space, we can always normalize each vector by dividing by its norm. It'll still be a basis, and it's known as an orthonormal basis. One example would be Rn, the standard basis for Rn. That's an orthonormal basis. Given a set of linearly independent vectors, v1 to vk, in a vector space, it may be desirable to make those vectors orthogonal, and also mutually orthogonal, I should say, and also normalized so that they have length 1. And the process for doing that is called the Gram-Schmidt process, which I've listed here. You start with your set of vectors, v1 to vk, and eventually you end up with the set of vectors u1 to uk that are mutually orthogonal, and if you like, you can make them normalize them to have length 1, and that would be the set w1, w2 up to w sub k. So you start with letting u1 equal v1, and then you can normalize that just by dividing by the norm. So that's first step is easy. The second step is you take u2 to be v2, second vector here, minus the projection of v2 onto u1, which you formed here. That's essentially v1. This is v1. And then you can normalize that. The normalization step is pretty easy. You're just dividing by the norm, but the making these things mutually orthogonal gets longer and longer, as you see. Then to get the third one, you take u3 to be v3 minus the projection of v3 onto u1 and a v3 onto u2. Then you can normalize that. I'll just do one more. To get u4, you start with v4, and then you need to project v4 onto u1, u2, and u3. So that this becomes very computationally difficult, almost impossible to do by hand. I mean, you can take a very simple example and for just a few vectors, but you typically want to use a computer program to do this. And then it goes all the way up to u sub k. So the same pattern repeats here. I'll just show you what this looks like for the case where you have two vectors in the next slide, just to give you a sense of what we're doing here with subtracting this projection. So I have an example here of the Gram-Schmidt process for two vectors. We start with v1 and v2, so this vector here and this vector here. And then the process tells us that u1 equals v1, so nothing complicated there. Then we need to form u2, and first we take the projection of v2 onto the line formed by u1. So we drop a perpendicular down, and then this vector here is the projection of v2 onto u1. And then u2 is v2 minus the projection. So it's this vector here. You can see that if you add this to this, you're just going to get V2. If you recall, when you add vectors, you line them up tail to arrow, and then you join from the first tail to the final arrow, and you get the sum. Okay, so that's and I should say that this vector u2 is, by the way we've constructed it, it's orthogonal to u1. So that's it for the two-dimensional case, or two-vector case. I was going to stop here, but then I thought, well, let me see if I can show you in 3 dimensions. So I have it on the next slide. I don't know, it's a little bit hard to see because I'm drawing in 2 dimensions, something that exists in 3 dimensions, but have a look and see if it helps clarify. Here's my example for 3 vectors. I'm assuming we've already done the first 2 steps. So we've created U1 and U2. We started with V1, V2, and V3, but we've created U1, which equals V1, and then we've created U2 using the process from the previous slide. And we want to find U3. So I've drawn V3 and assume it's not orthogonal to U1 and U2, so we need to do some work to compute it. So we need to compute these 2 vectors, these 2 projections of V3 on the U1 and V3 on the U2. So I have that here. We've extended U2, it's the line specified by U2, and the same thing for U1. And then we projected V3 down onto U2. And it may not be drawn to scale, but I'm claiming that's the projection, this red vector here. And then this is the projection of V3 onto U1. So we have these 2 here. And we want to take the minus of both of these. So the minus of this points in the opposite direction, and the same thing for this. And then we want to add them to V3, and we get U3. And this is where it gets a bit hard to see. So this is minus this one here. Just put it in the opposite direction, and then I put the tail, it coincides with the arrow of V3, and then I took the minus of this one, so going the opposite direction. Again, I lined up the tail with the arrow. So we're almost done. In order to add this, and this together, we go from this first tail to the final arrow, and we get this vector here, U3. So here's where it's hard to see. This is out. If you think of U1 and U2 on a plane, then V3 is pointing out of the plane, and this vector U3 is also pointing upwards away from these 2. And the claim is that this green vector U3 is orthogonal to U2, and it's also orthogonal to U1. And again, it's a bit hard to see, but if you imagine it sticking out, coming out of the screen towards you, then that would be the right way to think about it. Okay, so and of course, if we go into 4 dimensions, then we can't visualize 4 dimensions. So you just have to trust the formulas at that point that it's going to give you orthogonal vectors. All right, so that's the last slide in this lesson. I'm going to have several more lessons. The next one's on determinants, and see you there.